Okay, when you picture the end of the universe, what comes to mind? Like big explosions, a giant crunch, something, really
Well,
dramatic.
yeah, that's the typical image, isn't it?
Well, get ready for a bit of a cosmic plot twist. What if the universe just fizzles out?
Like a candle burning down.
Exactly. And what's really wild is that uh, recent science suggests this final fade might actually happen way, way sooner than we used to think.
Well, sooner in cosmic terms, of course. Still an unbelievably long time from now.
Right, right. Good point.
Mm.
But significantly shorter. Welcome, everyone, to the Deep Dive. Today, we are plunging into some seriously mind-bending research, stuff that's making cosmologists, well, rethink the whole lifespan of the universe.
Mm-hmm.
We've been digging into articles from PopMech Pro, Space.com, and CBS News. They're all honing in on this really fascinating study by astrophysicist Ino Felka.
Quantum physicist Michael Wondrak and mathematician Walter van Zwijlekam. A really interesting team-up.
Totally. So our mission today is basically to unpack this new cosmic clock, get a handle on the science, think like Hawking radiation, but maybe supercharged plus weird gravity effects, and figure out what it all means for, well, everything. But don't worry, you won't need an advanced degree to follow along.
That's the plan. So for the longest time, the universe's estimated lifespan was just staggering, something like 10 to the power of 1,100 years.
Which is, I can't even begin to picture that number.
Nobody can, really. It's almost meaningless. It's so vast. Think about counting every atom in the universe, then doing that trillions and trillions of times.
Yeah.
It's beyond comprehension.
Okay, yeah, got it. Huge number.
But now, this new research, it points to an end date closer to 10 to the power of 78 years.
10 to the 78. Okay, still sounds enormous.
Oh, it absolutely is. Unimaginably long by human standards. But compared to 10 to the 1100, it's a massive, massive revision in cosmic terms.
Wow. That really changes things.
It really does. It challenges some fundamental ideas about just how permanent things in the cosmos can be.
So a cosmic timescale downgrade, almost.
Yeah.
And this all comes from that work by Felke, Wondrak, and von Zwijlekam you mentioned.
Exactly. Their earlier work, back in 2023, started asking if Hawking radiation, the idea that black holes slowly leak energy and shrink.
Right, the particle pair thing near the event horizon.
Precisely that. They started wondering if that mechanism or something like it could apply to things other than black holes.
Okay, interesting.
And their latest work, published in the Journal of Cosmology and Astroparticle Physics, suggests yes. Their calculations indicate that even super long-lived objects, things like white dwarfs and neutron stars, aren't truly permanent. They'll eventually evaporate, too.
Evaporate, like just disappear.
Essentially, yes. Over truly vast timescales, they predict these objects will radiate away their mass. The mechanism they propose is related to Hawking radiation, but driven by what they call gravitational curvature radiation.
Okay, maybe let's quickly refresh on Hawking radiation first, just the basic idea.
Sure. So, near a black hole's event horizon, the point of no return quantum effects mean pairs of virtual particles constantly pop into and out of existence.
Right, fleeting things.
Yeah. But if a pair appears right at the horizon, one particle might fall into the black hole, carrying negative energy effectively, while the other escapes into space.
And that escaping particle looks like radiation coming from the black hole.
Exactly. And because energy is being lost, the black hole's mass has to decrease, albeit incredibly slowly. So it shrinks or evaporates over eons.
Got it. So how does that apply to, say, a white dwarf? They don't have event horizons.
That's the novel part. Falk and the team argue that you don't strictly need an event horizon. The extreme warping of space-time itself caused by the intense gravity of these other super-dense objects, white dwarfs, neutron stars can also energize these virtual particle pairs.
Oh, okay.
So even without a point of no return, the sheer gravity, the curvature of space-time can sort of boost these virtual particles into becoming real, escaping particles, carrying away mass.
So the gravity itself makes them leaky.
That's a good way to put it, yeah. It's a quantum effect, but triggered just by ultra-strong gravity, operating in a slightly different context than for black holes.
And you mentioned density earlier. Is that the key factor in how fast this happens?
Absolutely crucial. The denser the object, the stronger its gravity locally, the more space-time is curved, and apparently the faster this evaporation process occurs.
So denser things fade faster.
That's the prediction.
Yeah.
Their studies suggest things like white dwarfs, maybe supermassive black holes, even hypothetical dark matter halos might last for around that 10 to the 78-year mark.
Okay.
But neutron stars and stellar mass black holes, they're generally denser. They might only last about 10 to the power of 67 years.
Wow. Still immense, but noticeably shorter on that scale.
Definitely. And just for fun, they even calculated a theoretical evaporation time for, like, a human body.
Oh, no way. What is it?
Around 10 to the power of 90 years.
Huh. Okay, so we're safe for a very long time on that front.
I think it's safe to say other factors will get us long before universal evaporation does.
Good point. So even the most solid-seeming things eventually dissolve. But hang on, you said supermassive black holes might last as long as white dwarfs, but stellar mass black holes fade faster than white dwarfs.
Mhm.
How does that work if black holes are, black holes?
Yeah, that sounds a bit weird, doesn't it? It seems counterintuitive.
A little.
But the thinking goes like this. Black holes, despite their insane gravity, don't have a solid surface like a white dwarf or a neutron star does.
Okay.
These other objects, white dwarfs and neutron stars, they have surfaces that can absorb particles, redistribute energy internally, and then radiate that energy away from the surface. It's a complex thermal process.
Right.
Black holes lack that surface interaction. So while they emit Hawking radiation, some of those emitted particles can actually get pulled back in before truly escaping. This reabsorption acts like a bit of a brake.
So they kind of recapture some of their own leaked energy.
Sort of, yeah. Which means, compared to another object of similar density with a surface that's efficiently radiating, the black hole might actually evaporate a bit slower overall.
Huh. Okay, that makes sense. It's subtle.
It's definitely a nuanced effect they're proposing.
So pulling this all together, the big picture isn't a fiery finale or crunch. It's just a slow fade. A quiet dissolving into particles and radiation.
That seems to be what this line of research points towards, yes. Over these almost unimaginable timescales, all the structures we see, stars, galaxies, clusters, they would eventually just dissipate into a vast, cold, incredibly dilute soup of fundamental particles.
The heat death scenario, but maybe happening sooner and via this specific evaporation mechanism for everything.
Kind of like that, yes. A universe slowly emptying out.
Which, wow, really puts our own cosmic backyard into perspective. We worry about the sun engulfing Earth in, 8 billion years?
Roughly, yes, give or take.
And that sounds like forever, but compared to 10 to the 78 years, it's nothing. It's literally the blink of a cosmic eye.
It absolutely is. The scales are just staggering. Which brings up the inevitable question, right? If we, humanity, won't be around to see this final fade, why does it matter? What's the takeaway for us now?
Yeah, the so what question. Well, I saw a really nice thought in that space.com article. It wasn't about achieving permanence, because maybe nothing is permanent. Instead, it suggested the meaning might be found in, and I'm paraphrasing slightly, the fleeting brilliance of asking questions while the stars are still shining.
Oh, I like that.
Yeah, it's about the act of discovery itself, trying to understand this incredible universe while we're here, while there's still a universe to understand,
That resonates. It frames science not just as finding answers, but as a meaningful activity in its own right, especially in the face of such ultimate cosmic impermanence.
Exactly.
And it's also crucial to remember, as this CBS News piece touched on, that this isn't necessarily the only possible ending. Our understanding is still evolving. There's ongoing research into dark energy, for instance.
Right, the stuff driving the universe's expansion.
Yeah, and we still don't know its ultimate behavior. Could the expansion slow down, stop, even reverse into a big crunch? It's still an open question.
So this evaporation scenario is one strong possibility based on current physics, but there are other cosmic mysteries still unfolding.
Precisely. It's a major potential pathway based on this new theoretical work, but cosmology is always a work in progress.
Okay, so let's try and sum up our deep dive today. The big headline is, the universe's ultimate end date might be much, much sooner than we thought, revised down from maybe 1100 years to around 1078 years, still an eternity, but cosmically a huge shift.
Right, and this comes from the idea that not just black holes, but all massive objects, white dwarfs, neutron stars, everything will eventually evaporate. It's through a process like Hawking radiation, but driven just by the intense curvature of space-time their own gravity creates.
And the key factor controlling how fast they evaporate seems to be their density. Denser things go quicker.
Exactly. White dwarfs around 1078 years, neutron stars maybe at 1067. It paints a picture of a gradual fade-out for the cosmos.
Which leads us, and you listening, to maybe a final thought to chew on.
If even the most massive, seemingly eternal structures in the universe are ultimately destined to just dissolve into nothingness over these vast timescales, what does that really tell us about existence? About permanence? about our own brief moment in this immense cosmic story.
A pretty profound question to end on. Thank you so much for joining us for this deep dive into the universe's potential expiration date.
Yeah.
We really hope it sparked your curiosity.
Hope you found it interesting.
If you enjoyed this journey into the cosmos and you want us to tackle other big questions or fascinating science, please do hit like and subscribe. And definitely drop your suggestions for future deep dives in the comments below. We love hearing what's on your mind.
We really do read them.
Absolutely. Oh, and just a quick note, we sometimes mention products or services we find useful or interesting. If you happen to check them out through links we provide, some might be affiliate links, which just means it helps support the show, allowing us to do more deep dives like this at no extra cost to you, of course.
Helps keep the lights on for exploring the cosmos.
Exactly. So thanks again for listening. Stay curious and stay tuned for our next exploration into the unknown.